Welcome to Case Western Reserve University in beautiful Cleveland, Ohio. I am Professor Roger Quinn.
And I'm Dr. Richard Bachman, and we are faculty in the Department of Mechanical and Aerospace Engineering in the Case School of Engineering.
And we are going to give you a virtual open house. On the bottom left, you see a photo of a team, and there's a car there. This was the team that competed in DARPA's Urban Challenge. DARPA's Urban Challenge was a jumpstart for autonomous vehicles. It was the Urban Challenge was done in 2007, and that car there we call it Dexter. And it was one of the first autonomous vehicles that could actually drive through city streets, obeying all the traffic laws. The competition, if you won it, you'd win $1 million. We didn't win it, but of course it cost about $1 million just to compete. So it wasn't about the money. It was about the challenge. And that car is now here in University Circle in the museum, the Crawford Automobile and Aviation Museum. The picture on your right, I should point out that DARPA is an advanced research projects agency. And the picture on your right is as one of the cases where rockets taking off. This is our department's mission. The bottom line is our first priority is education of students, preparing them for leadership roles and conducting work in society, benefiting society. Our second goal is research. But the thing is, those two things, education and research in our department, are tied tightly together. The research keeps the faculty fresh for the education mission, and a lot of our undergraduates actually get involved in our research as well. What we do in the department is to emphasize fundamental engineering. What's hot now is not probably going to be hot in 10 years, and certainly not in 50 years. But the fundamentals, if you understand the fundamentals, if you really learn the fundamentals, then you'll be able to work on any of those things. What's hot now, 10 years from now, 50 years from now. So you'll be able to contribute to society in a gainful employment if you understand the fundamentals. So we have our students get jobs in various places all over the country. And a number of them go to graduate schools as well to earn masters and PhDs. Mechanical engineering can be summed up with a simple phrase that we design and manufacture things that move through time and space. I should say that also applies to aerospace engineering. We have two majors, aerospace engineering and mechanical engineering. We also have a streamlined mechanical and aerospace double major, which can be earned in 4 years. Very popular. We also have a BS-MS program, which is you can complete, get a bachelor's degree and a master's degree in mechanical and or aerospace in 5 years or less. The fact is, I've had a number of students who've done it in 4 years because they cleverly use their AP credits, and they use their scholarship then to pay for the master's classes, master's tuition. Typically, though, it's more like 4.5 years. Our undergraduate enrollment is about 350 students. We graduate about 100 students per year. And here you see our double majors is pretty popular. Like 25 out of the 100 get both do the double major mechanical and aero. 20 to 30% of our students typically co-op, so they go out for 7 months in the industry and they earn real money, and they typically come back and are better students and their GPAs go up. So we have a co-op office that helps students find those jobs, and we have companies that actually really like our students and come on campus to recruit them. And I'd like to point out that I've been here over 30 years, and I can tell you in up and down economies, our graduates always find jobs.
Before we go, it's worth noting that 7-month co-op stint involves a summer and a semester. So it's either a spring semester and a summer, or a summer and a fall semester. As such, you will push back your graduation date by that semester that you are not here taking classes. You'll have to make that up later. But while you're on co-op, you're enrolled in a class that counts as full-time enrollment. So all of your scholarships, both on campus and off campus, do defer to the following semester. That's never a problem. And any of your student, it doesn't count against your student loan grace period for when you have to start paying those back. In addition to co-oping, a lot of our students also do internships. Some of them don't want to add the time to graduation, but they really also want to get some experience while they're here. And a lot of them, a significant number of them, do internships, which is just a summer, 2.5 to 3 month stint. Those you're more on your own to get, but they're not terribly hard to find, considering any company that you want to work for has a website, and you can go there and look for career opportunities, and they probably list any internship openings they have.
Our students typically do not have a problem finding summer internships and co-ops. And like I say, so often they come back and do better in school. And
a lot of them come back with full-time job offers already for the following year, even if it's 8 to 12 months away. A lot of them come back with already knowing that they have a full-time spot with that company.
And this takes us back to the reason this is true is because our students learn the fundamentals and can also learn how to solve problems. I didn't point that out earlier, but we emphasize the fundamentals, learning the fundamentals of engineering, but we also try to teach problem solving. So many of our classes are about solving problems. Given some information, you have to go out and find more information. You have to ask questions, figure it out, and then solve the problem. And that's what employers just absolutely love. So often, employers will call us and say, please send more. Now, moving on to the department faculty, well, we have 18 faculty, 4 female faculty members out of those 18. And then we have a couple emeritus faculty who are in academies. We have more than 20 research associates, research faculty, postdoctoral fellows, and out of this, we also have 7 professors emeritus. It turns out that there's 2 of them that are still here they're generally here every day doing research. So even though they've retired, in fact, there's 3 of them now, I think about it, 3 of them who are emeritus, who are still actively here and working with students. ThinkBox is truly unique. There's nothing like it in the rest of the country, and probably not in the rest of the world. It's a 7-story building. It's just a few minutes walk here. You don't even have to cross the street to get there. Just cross a playing field and through a gym, and there you are. ThinkBox, a 7-story building. Here you see this like a mechanical engineer, aerospace engineer's dream place, because you can make stuff there. You've got lathes, milling machines. You can do fabrication, welding, wood shop. Many times our seniors do their senior projects there, and you can do student projects all kind. You can walk in the very first day you're here as a freshman, walk in there and do some project. Of course, they want to train you up on the machines first, which is good. But then you can, as you get trained up, you can use just about anything. Well, you can actually use anything, and you can start out by just making gifts for your family. And also, you should point out that as a student here, you don't even pay for any of that except for the material you use. You don't have to pay for being trained up. You don't have to pay for the machine time. You can do it yourself, just paying for the material. Also, we have in ThinkBox, there's state-of-the-art 3D printers, CNC, computer numerical control machine tools, and various other things. So you can go in there and you can design. We have design software. So you can go in there and design up things and fabricate, assemble. It's, like I say, it's a dream world for our students. And our students take advantage of it.
But the coolest thing about ThinkBox isn't necessarily the machines. The machines are cool, don't get me wrong, which also include a laser cutter. We actually have a CNC controlled, computer numerical controlled sewing machine, so you can sew logos on things to put on your devices, on your things that you're building. But in addition to the machines, this is actually a 7-story building that's designed to be basically sequential from the ground floor up. So the ground floor is dedicated to ideation, and then past that you get to design work, and then above that you get to fabrication and assembly, and at the top floor, well, I'll let Roger tell you more about the top floor.
Okay, and the top floor is actually an incubator. So you can start out with some idea for a project on the first floor, and you work your way through building prototypes. And at the top floor, you now can start a company, and you can actually get free legal advice. And it actually works. We actually have students who have done this. We have a couple of my students actually started a company, and they've now hired, they have millions in venture capital, and they've hired, last I knew, more than 30 workers. So this is it's a fantastic facility, and like you say, there's nothing like it. For example,
well, I know I'm personally aware that a couple times, maybe 2 or 3 times a year, other universities send delegations to our ThinkBox to see how we designed our makerspace, to get ideas, and many of them model their makerspace off of our makerspace.
it was a 7-story building that was actually a storage facility that's been completely redone from the bottom floor to the top. And it's really fantastic. So when you do get an opportunity to come and visit us in person, this is someplace you got to see. Now, moving on to the curriculum. Well, there's general education requirements, university and School of Engineering general education requirements. For example, there's what we call SAGES. SAGES first seminar, and then there's 2 SAGES university seminars. The SAGES first seminar, you take that, you show up as a freshman, you choose out of a long list of possible courses. But the idea is you're supposed to be learning communication. You're supposed to be learning both oral and written communication. So it's a small group, typically 17 students. And there's a whole bunch of, instead of just learning about Byron or something, you could learn about Byron if you're interested, but if you're interested in something else, there's a wide range of options for these first seminars. For example, Rich teaches a SAGES first seminar on.
That's right. So the class covers subsystems and how the technology involved in automobiles, aircraft, and power generation and distribution. So we learn some of that on the technical side, which is fun, and exploring new things there. But then also we look at for sort of a basis for a lot of our writing, we look at how popular opinion or how people's perception of the technology can affect whether the technology gets adopted or abandoned. Any parents who are out there listening will understand this question. Why did VHS beat Betamax? And if you don't get it,
everybody knows that Beta is better than VHS.
And if you don't know the question, don't know what that means, just go look it up. It'll be fine. Or ask your folks, I guess. But anyway, so one is one that we use some of is Ralph Nader wrote a book years back about the Chevrolet Corvair. That it was basically, he thought it was a death trap. Everybody I know who's owned one loved the car.
They were fantastic.
It actually had a significant impact on Chevrolet's ability to sell the car. His book. So we talk about that as far as the other side of again, fodder for writing and oral communication.
So anyway, this is a university. You're not just going to come here and just take technical courses. So there's 4 breadth courses outside of engineering, natural science, and math that you're required to take. So that's an opportunity, though, if you're interested in a minor. So you can put those 4 breadth courses together with another course or 2 and turn into a minor if you're interested in, for example, a lot of our students do dance and music, and there's some instrument that they're interested in. Also, you can do minors in economics. Of course, there's physical education requirements. And then you get into the technical stuff like our engineering core requirements. So you have to take certain courses like the prep courses like math, chemistry, and physics. And then, of course, there's a fundamental engineering courses. There's 4 of them that you're required to take that prepare you for the classes inside our department. And then after you're done, well, in addition to all of that, there's, of course, the major specific courses, which is why you'd be coming here to our department anyway. So if you're an aerospace engineer, these are the courses you take. And if you look, you see columns. It's first year, second year, third year, fourth year columns. And you'll also see within those columns, you see two columns actually, and one's fall semester, the other spring semester. I don't expect you to memorize this. There won't be any quiz afterwards. Just pointing out that this is a roadmap. This helps you get through the degree, through the aerospace degree, not messing things up in terms of co-requisites and prerequisites. The idea is this tells you what courses you have to take in what order so that you can be successful.
In addition to that, it's sort of if you will, a covenant between the student and the department that if you take each of these courses in the semester offered, they will be offered in the semester they're listed here. They will not conflict with each other. And so if you take them all in that order, you're out of here in 4 years with your degree.
And here's the one for mechanical engineering. All the things we just said, of course, go for this as well. And these things are posted. If you do come to CASE and into our department, these are fantastic because, as Rich says, it's like a covenant. You do this in this order, and successfully, you get a degree. So next, we talked a bit about, okay, the primary goal, primary mission of the department is education, but we faculty, we also do research. We have particular things that we do. We're a fairly small department. These are a list. This is a list of things we're really good at. There's robotics. Rich and I are into robotics, and there's another faculty member in robotics as well. In particular, bio-inspired robotics. And then there's biomechanics. I should point out that the robotics program in this department is about 30 years old. The biomechanics group is actually, that specialty has been here for more than 40 years and going strong. They used to be very strong, well, we still are very strong in joint implant research and in bone mechanics. But now the newer faculty are much more into and experts in growing artificial organs, for example, and blood assays. So inexpensive ways, testing, so that you can determine if people have a particular blood disease. So inexpensive is important, for example, for implementation in Africa, which is what's being done. We also have a strong aerospace component, and in particular microgravity. And we actually had some of the first experiments, I think the first experiment, microgravity on the space shuttle back in the 80s. And we still have faculty still working in microgravity. Questions about like how does flame spread in microgravity, which is really interesting. We also have NASA just on the other side of town. NASA Glenn Research Center is on the other side of town. And over there, they have the most wonderful facilities, giant wind tunnels, multiple wind tunnels. And our faculty have the opportunity to do research there in collaboration with NASA personnel. They also have a 500-foot deep hole in the ground. It's basically a silo, and they can pump the air out and do drop experiments. So you can actually do microgravity drops. We also have the Great Lakes Energy Institute, and primarily our research here in energy is in wind turbines and solar panels. We have a very strong group in solar panels, and in particular, how to make them better, how to make them last longer, and be more efficient. And that's across multiple departments. It's actually in the physics department is also strong in that. We also have a group that works on impact material properties in terms of impact. For example, cars running into each other. We're talking, high speed. How does metal behave? It's not just a linear deformation. We're talking just tremendous plastic deformation. But we also have, we've been very strong for 50 years in what we call the thermal and fluid sciences, which includes energy and aerospace. But now we have a fire center. We also have a faculty member that works in detonation kinetics. And we also have faculty that work in heat transfer thermodynamics in terms of how machinery works. Power generation machinery, for example.
Keep in mind that Dr. Quinn mentioned that we have the NASA facility right across town, and these are the areas that our faculty are doing research. That means there are also areas that the undergraduates can get in and do research, right? All these faculty they have the research project themselves. They have 1 or 2 or 10 graduate students, and each of those graduate students have some part of the project that it's not a good use of their time. They're not going to learn anything from doing it. It's a great opportunity for an undergraduate to get a hold of something, learn something about a bigger project, and be part of something really cool. There were some other cool things that some of our newer faculty are doing. We're doing multi-scale physics, and that is, so we're modeling systems, and basically you might model certain interactions on a larger scale where you can just have a governing equation that you follow, but then sometimes let's say it's blood flow through arteries. If it's when you might be looking at interactions between the actual liquid blood and some of the actual cells, you might have to do basically a simulation that looks at interactions right between the fluid and the surface itself. So it's other interesting things going on. So
yeah, we actually in our robotics labs, I think we typically have 30 to 40. Well, I know. We typically have 30 to 40 undergraduates working out in our labs just about every year in robotics.